we're going to look at another topic that we didn't have time to do in class on conics, but is very handy. And that's what are called the latera recta of conics. The plural is called the latus rectum, which always gets a laugh. And the length of it is called the focal diameter. And you'll see, especially that last term, why that's true. So what we're supposed to do is we're supposed to take our conic, here it's a parabola. We're supposed to draw a segment through the focus perpendicular to the axis with ends on the conic. In this case, that's AD. And in the case of, that's called the latus rectum in this case. And in the case of a parabola, it's very easy to figure out how long that is. Remember the definition, the geometric definition is A is on the parabola if the distance AB is the same as the distance AG. But if we're talking about this point that's at one of the ends of the lattice, that's supposed to be perpendicular to the axis. Therefore, it's parallel to the directrix. And if AB is the same length as AG, we've got a little square here. And we've got a square BDF, and I guess I don't have this point marked. And we've got a rectangle that's twice as wide as it is tall. Remember that P is just the distance from the vertex to B, and it's also the distance from the vertex down to the directrix. So AG is going to be 2P, and then because it's the same as AB, this is going to be 2P. So I've got the 2P marked here, but it's also AB. This is 2P. This is P. This is P. This whole thing is 2P. Everything is either P, 2P, or 4P. And so the length of the whole lattice, and that has length 4P, and that's called the focal diameter. Okay. And so you just can remember that all these dimensions are the smallest dimension is P, the medium dimension, which is like AB or AG, is 2P, and the biggest dimension is 4P. That's very useful because it gives you a very easy way to plot 2 points on the parabola accurately if you have the focus. So if you have the vertex and the focus, just go from the vertex, go to the focus, and then go twice as far out to make a little 2:1 ratio rectangle with that point and the focus and the vertex, and go in either direction by that 2P distance, and you've got 2 precise points on the lattice. The other thing is special about the lattice, and as relates to the reflection property, I've still got that tangent line drawn in here. That's exactly something where an incident light ray is supposed to reflect to the focus. Well, if the focus is at the same height, well, it's reflecting 90 degrees, so that means that the tangent line has to have slope 1 there. It has to be at a 45-degree angle. So that's another reason why it's good to plot these 2 special points on the parabola if you're interested in reflection. It gives you a very nice couple of points that are easy to plot precisely, and you can sketch in very precisely, if you want, that 45-degree tangent line. So it's a good reality check on if you're thinking about the parabola right, if you're drawing it right, and if you're thinking about the reflection property correctly. So let me turn to a more complicated issue of how you figure out the focal diameter and the properties of the latera recta, because there will be plural ones now, for an ellipse and a hyperbola. It's actually a very pretty story, but the algebra is significantly more complicated. For an ellipse, the latus rectum is going to be when the main axis, the major axis, is horizontal, the latus rectum is going to be going perpendicular to that axis. It's going to be vertical through C, there's one of the foci, and E, it's also going to come out the other side, but I'm going to focus on just figuring out the length of half of the lattice. And that's just exactly what is the y coordinate of a point that is right above the focus. Just exactly if you go for the perpendicular direction, the minor axis direction, if you will, from the focus and hit the ellipse. And that's just the y coordinate of that point, so I'm going to call it y. Okay, so we're looking at the point with coordinates c comma y. So we set x to be c. That's the x coordinate of the focus because that's our usual letter for the location of the focus. That's how far it is from the center. And we want to figure out y as a function of a and b. And the cool thing is that we actually can rederive the equation for c in terms of a and b at the same time if we use not only the equation of the ellipse and the geometric formula, or the geometric description, which we use the geometric description in the other case, so that shouldn't be super surprising. So the equation of the ellipse, so this is going to be more algebraic, as I said, but it's very cool how it works out. So this is the general equation for the ellipse. Of course, it's centered at the origin because this should all work even if we're shifted, but I shouldn't introduce that complexity. Okay, and so I'm going to take that and I'm going to set x equal to c. And the cool thing is this will work even if we don't actually know a formula for c yet. We're going to get them simultaneously. So that's one part of the story. Okay, the other part of the story is that that geometric formula, indent that a little bit, or the geometric definition, I guess should say, is that the distance, the sum of the distance from E to C and from E to D should be equal to 2a. We haven't focused on that too much, but you've seen it, and we're going to use it in a very nice way now. So the distance from E to C is obviously y. The distance from E to D, because this is a right triangle, we can figure that out. It's the square root of the leg here, which is just 2c squared, which is 4c squared. So the quantity 2c squared. So that's 4c squared, and then plus y squared. That should all equal 2a. Okay. So that might look a little intimidating, but the very natural thing to do to eliminate that square root is what you do. You leave that on one side, and you get 2a minus y. You square both sides, and you get a nice little break, which you often get in conics, which is, we'd think that'd be a quadratic in y, but the y squareds cancel. I need a little more room there, don't I? It's going to be mostly algebra from here. Okay, so that's cool. And then the 4's cancel. So the y squareds go away, the 4's go away, and I get c squared equals a squared minus, give me one sec, minus ay. And if you like, I can factor the a out there. That's really pretty slick. Okay. So it's just one relationship between c and y if a is known, and b seems to have just kind of taken a powder here. But that's where we can plug it back in here. Hey, look, c squared. There's a very nice place to put that in there. And so I'll copy that down, but I'll replace, let's display that. And so I'm just going to call that a times a minus y. And then we're really pretty much home free. Okay, let's just go ahead and distribute that. I guess I could have left it as a squared minus ay, but whatever. Okay, and then I'm actually going to separate that numerator. Wait a minute. That's a squared over a squared minus ay over a squared. Let me just cancel a little bit in place here. Hey, this is getting pretty good. A squared over a squared is 1, and that cancels the 1 on the right-hand side. Hey, that's really cool. We're getting very simple here. That's equal to 0. Or in other words, you know what? Let's just pull this over the other side. And I can cancel out a y. I know it's not equal to 0. Very dangerous if you don't know something is non-zero, but I know it's non-zero. And so I can cancel out that y. Pretty dangerous step. Maybe not a good thing to encourage you to do, but here I know it was non-zero. That's going to be legal. So there's that half length. That would be the focal radius. So the focal diameter, and the length of each of the Latera Recta is 2b squared over a. Very handy to note. Okay. So again, one of the usefulness of that is if you're sketching an ellipse, and you know A and B precisely, then you can get 4 points on the ellipse, 2 here and 2 over here, very precisely, without a lot of square roots and plugging in and random points, stuff like that. It's just a very nice formula in terms of B and A. It's just B squared over A. Now, I promised you could actually get C out of this. And of course, we can, because we just go back to here. And let's see, I guess really this form is better. The factor form isn't really that useful. And so I'll just get this. It shouldn't be a surprise, but it turns out this is really particularly nice in the hyperbola case, which we'll do in a second. Okay, so y was b squared over a. Oh, hey, the a's cancel, and I get a squared minus b squared. And that is this sort of Pythagorean relationship between the semi-major axis, the semi-minor axis, and the focal length of the length of the segment from the center to the focus. Okay, so I think that's cool. I think it's even cooler that it works for hyperbolas. Let me show you that in a sec. So for the hyperbola case, I'm going to go through it pretty quickly because it is super similar, which isn't too shocking. The hyperbola algebra and the geometric definition are related to the ellipse one just by changing signs. So something's pretty good's got to happen here. And so now, once again, we're picking the point C comma Y. That's this point E now. That's so CE is going to be 1/2 of that, one of the latera recta, and that's the Y is going to be half the focal diameter. And now we just need to change the sign of that. Change the sign of that. I'm going to go through this pretty quickly, but that's a good place for the pause button, just to compare to the picture and say, okay, is this still making sense? The geometric definition, remember, you have to be a little careful with that. That is the difference of the two distances. So you pick a point and you determine whether it's on the hyperbola by looking at how far it is to one focus, looking how far it is to the other focus, taking the difference of those. That should always be the same constant. And it turns out, you have to put it here. And that should, again, be 2a. So that's where we're connecting with the geometric definition of the hyperbola. So now this is just going to change to a plus. This is going to change to a plus. This is going to change to a plus, but the y squared still cancel. The 4's still cancel. It is super similar. I was tempted to do this with all plus or minuses, but I think that can get a little confusing if you're not used to sort of systematic use of plus or minuses. This is now a plus. And what did I do here? A squared over a squared is 1 still. That's now a plus. The 1's still cancel. I can still move. Remember, this was y squared over b squared equals y over a. Now it's going to be a minus. Oh, wait. That doesn't make any sense. I didn't change this one too. Aha. Yeah, that makes more sense. Okay. Because we actually get the same exact answer. I was like, wait a minute, it's supposed to be the same. So this sign changed and this sign changed, and they exactly compensate. You still get exactly the same thing here. You can still cancel the y's because you know they're not 0. And it's exactly the same formula. So that may be a little surprising that nothing changed. Although if you think like it's a length, it couldn't have become negative. And so it's actually the focal diameter in both cases is 2b squared over a. Very nice to know. So again, a very nice thing if you want to plot a couple of easy but very accurate points on the hyperbola to get a sense of just exactly how bendy it is, how closely is it approaching its asymptotes, things like that. And then we can go back, of course, to c squared. This is something that's rather tricky to actually come up with, and like our trig precal book just totally does not even come up with it at all. The algebraic relationship between a, b, and c. It's still a Pythagorean relationship, but it's not as obvious as for the elliptic case. And this is really the best proof that I know, that it's just going to be, we plug this back in, and we have now a squared plus ay. That's where there was a different sign. And then that's a, plus a times b squared over a, and we get exactly this nice relationship. The Pythagorean relationship, c squared equals a squared plus b squared. Seems like there should be a simple right triangle there, but I don't know of one that sort of shows you there's an obvious simple right triangle that creates that. But this is nice because it was a certain amount of algebra, but it's the kind of algebra that gets a little complicated for just a little bit and then just collapses into beautifulness. And it gives you a 2-for-1, that it's giving you this very interesting point at the end of the lattice, giving you that focal diameter, and also giving you what the relationship between A, B, and C are. So I like it a lot.